Lesson 3.1, Key Questions. First question is this: in what circumstances will the motion of objects change? And our next question: what sorts of rules do objects follow with regard to changing the state of motion? Well, in our previous chapter we learned about static equilibrium, where things stay at rest if no net forces act on them. No net forces, no motion. We also learned about dynamic equilibrium. In dynamic equilibrium, things do have motion, but they don't have any net forces acting on them either. And the motion is constant. That's a key point. We're going to explore changes in motion, going from states of not moving at all to moving, and also from a state of motion to a state of rest. Let's get started. The first case that we're going to explore is one where an object is at rest and then it will begin moving. We've got our muscle man here. He's going to be used to apply forces. We just need an object. I have chosen a little 7th grader for our object. And so let's see what happens when we apply a force to the little 7th grader. Currently the 7th grader is not moving. I think you would agree with me on that. And if we apply a force to the 7th grader, sure enough, she starts moving. Well, that is certainly interesting. All right. So we have a 7th grader in motion. Let's consider what happens when we stop pushing. Aha! So we've observed two things. We've observed a 7th grader at rest going into a state of motion. What was required? A net force. Now we've seen that once the 7th grader was moving, that when we stopped pushing, she slowed down and came to rest. But wait, there's more. What you just saw was what you normally would see in your daily life. With this computer simulator, I can control some things that you normally would not be able to. Namely, friction. I'm going to take and set friction to none. Zero friction. And as I do that, the picture changes and it looks kind of like it's icy now. The surface that the girl is on is icy. Ice still has friction. Okay? The only thing that I can think of that doesn't have any friction is outer space. And so maybe I should define what friction is. The friction is, according to this lesson anyway, we're gonna say that friction is an interaction between an object, such as a 7th grader, and the surfaces or matter that the 7th grader is in contact with. So if the 7th grader were flying through the air, friction would be the interaction between the 7th grader and the air. Right? There's an interaction there. And if they're sliding across the ground, then the 7th grader is interacting with the ground with some kind of friction, we say. But now I've taken that friction and I've reduced it to 0. So let's take a look at what happens now when we apply a force to an object at rest, and then we stop applying the force. Okay? All right? As before, we have a force applied to the girl, as shown by our vector, and she begins to move faster and faster. Let's take the force away and see what happens. The girl is moving, and she continues to move in what looks to be dynamic equilibrium, or in other words, at a constant speed. So in the absence of friction, objects that are moving tend to stay moving. And so we have here, I think, a basic rule that we can state at this point, that objects at rest tend to stay at rest. The girl, when she was sitting there, continued to sit there until we put a force on her. And objects at rest, or rather objects in motion, tend to stay in motion unless what? Well, let's bring our muscle man back into the picture and see if we can slow her down if we apply a force. We apply a force to the girl, and sure enough, it does appear as though she's slowing down. Okay, muscle man, you gotta work a little bit more here. A little bit more. Alright. Still in motion. Very slowly. You can see how friction here. Without any friction, she stays in motion. Let's try it. There. We've stopped the girl. So an object in motion tends to stay in motion unless a force acts on the girl. And that would be a net force, right? So we have a net force needed to get the object moving, and we have a net force needed to stop the object once it is in motion. Next question. What sort of pattern can we see here? Is there a pattern? Do all objects obey this rule? Do all objects, when you apply a force to them, start moving in the same way as all other objects? And once they're in motion, can we change their state of motion in the same way that we would observe with all objects? Let's take a look at our girl. We've added a speedometer to the simulator, and I'm also going to take a look here at something called mass. Right, the mass of the girl is 40 kgs, or 40 kilograms. It's a unit of mass. We're going to put a force on here for approximately 5 seconds, and we're going to see what happens. All right, let's try it. 1, 2, 3, 4, 5. All right, so in 5 seconds, there's no number here associated with the speed, but we can see basically where the dial is. It's about 3.5 units, we'll say. There aren't any numbers, but 3.5 units. Remember that. Remember that. Okay? Because now we're going to try this again with another object. Okay? The girl is 40 kilograms. 40 kilograms. So the girl, force applied to her for about 5 seconds, got to a speed of about 3.5 units. Let's now try the same experiment with an accountant. Now let's note that the accountant is 80 kilograms, which is twice that of the girl. Let's apply a force to the accountant for a time period of approximately 5 seconds. An equal force, I might say. All right, here we go. 1, 2, 3, 4, 5. Objects in motion do tend to stay in motion. It doesn't seem to matter if you're a junior high girl or an accountant. That rule seems to apply. However, the speed is different. The girl's speed was 3.5 units, and here we see the accountant's speed is somewhat less. Not quite 2.5. We're a little bit over time. I like to shoot for about 10 minutes or less for these, but let's try a prediction. What do you think is going to happen if we put a force on this refrigerator, which is 200 kilograms? Same amount of force, same amount of time. Let's see if you made the correct prediction. 1, 2, 3, 4, 5. What we seem to have here is a relationship between the mass and the force. More massive objects tend to resist a change in their state of motion more than objects of less mass. So, in other words, applying the same force to an object of less mass will cause it to change its motion greater than an object of more mass. Here we see that the speed is about 1/2 unit, or whatever. I can't remember what our units are. But at any rate, it's slower. So thank you for joining me. Please remember to answer your questions at the end.